Acids and bases. So when you first put a Sour Patch Kid in your mouth, it tastes sour. The taste is caused by a white powder coating, a mixture of citric acid and tartaric acid. So those acids from a Sour Patch Kid combine with saliva in your mouth and they produce hydrogen ions. Those hydrogen ions react with protein molecules on your tongue inside of your taste buds. Protein molecules change shape, sending an electronic signal or a nerve impulse to your brain that you experience as a sour taste. James Bond often carries an acid-filled gold pen. Bond's pen is made of gold because gold is one of the few metals that is not dissolved by most acids. When Bond is imprisoned, he squirts some acid out of his pen into the iron bars of his cell. With enough acid, it would be possible to dissolve the iron bars of a prison cell, but it would take a lot more acid than the amount that fits in a pen. And here, you can see a small piece of aluminum placed in hydrochloric acid dissolves away in about 10 minutes. So Arrhenius acids. There's different definitions to what an acid is. So the first definition is Arrhenius, which says an acid solution contains an excess of hydrogen ions. Some properties of acids include a sour taste. It turns blue litmus paper red. It dissolves most metals. So we use litmus paper to test pH, and this gives us a rough idea of the pH. If you have a swimming pool or a hot tub or even a fish tank, there are pH strips that you can dip in the water and it will cause a color change on the test strip, and then you can look at the color and compare it to known pH colors. This is also how urinalysis works. So if a patient comes in and they have urinalysis performed, although we do put it on an actual instrument to read the urinalysis pH of the urine, we can also just dip it and compare the color to the side of the container of the dipstick urine test. And then we can determine the relative pH based on the color change on that test strip. So with an acid, it's going to cause litmus paper to turn red in color. Different types of pH indicators will have different types of color changes, but litmus paper will turn red in the presence of an acid. So an acid produces hydrogen ions in aqueous solution. So HCl is a covalent compound and does not contain ions, but in water, HCl ionizes to form H plus ions and Cl minus ions. Hydrochloric acid is found in most chemistry laboratories. It's used in industry to clean metals, prepare and process foods, and refine metal ores. It's the main component of stomach acid, and hydrochloric acid doesn't actually break down the food itself. Hydrochloric acid decreases the pH of the stomach, which activates enzymes in the stomach, and the enzymes are what actually act on breaking apart the bonds of the food molecules. A lot of people think that the acid corrodes the food in your stomach, and that's not the case. The acid that's secreted decreases the pH of the stomach, which activates enzymes, and then those enzymes break down your food. Hydrochloric acid, because it changes the pH of the environment, that pH is a harsh environment for bacteria to live in, so it can kill bacteria. The sour taste associated with indigestion is caused by the stomach's hydrochloric acid refluxing up into the esophagus. Acetic acid forms in improperly stored wines. The word vinegar originates from the French vin aigre, which means sour wine. Acetic acid is an example of a carboxylic acid, an acid containing the COOH group of atoms, known as the carboxylic acid group. We often find carboxylic acids in substances derived from living organisms. Other carboxylic acids include citric acid, the main acid in lemons and limes, and malic acid, an acid found in apples, grapes, and wine. Bases have a bitter taste, they feel slippery, and they turn litmus paper blue. All of these consumer products contain bases. Bases feel slippery because they react with oils on your skin to form soap-like substances. Soap itself is basic, and its slippery feel is characteristic of bases. Some household cleaning solutions, such as ammonia, are also basic and have the typical slippery feel of a base. Bases are less common in foods than acids because of their bitter taste. Our aversion to the taste of bases is probably an adaptation to protect us against alkaloids or organic bases found in plants. Alkaloids are often poisonous. The active component of hemlock, for example, is the alkaloid conine, and their bitter taste warns us against eating them. Some foods contain small amounts of base. Coffee is acidic overall, but bases present in coffee, such as caffeine, impart a bitter flavor. Sodium hydroxide and potassium hydroxide are found in most chemistry laboratories. They're used in processing petroleum and cotton, and in soap and plastic manufacturing. Sodium hydroxide is the active ingredient in products such as Drano that work to unclog drains. Sodium bicarbonate can be found in most homes as baking soda and is an active ingredient in many antacids. When taken as an antacid, sodium bicarbonate neutralizes stomach acid, relieving heartburn and sour stomach. So which type of solution would have a sour taste and turns blue litmus red? An acid. Which of the following descriptions identify each as a property of an acid only, a base only, or either? So go ahead and pause the video and work through this, and then we'll go through this together. Okay, so a bitter taste would be a base, reacts with active metals to generate hydrogen gas, an acid. Sour taste, an acid. Is slippery, a base. Undergoes neutralization, either one of them can be neutralized by the other one. And turns blue with litmus, a base. So in the Arrhenius definition, it said that an acid has an excess amount of hydrogen ions. The Bronsted-Lowry acid and base definition is similar, although it says that an acid is a proton donor, while a base is a proton acceptor. So if we look at this problem right here, and you will be presented an equation on the exam, and it will ask you to identify what the acid, base, conjugate acid, and conjugate base are. The easiest way to do this is to look at the anion. So we have Cl on this side and Cl on this side. What happened when we moved from the Cl on this side to the Cl on that side? Did it gain or lose a hydrogen? So it lost a hydrogen. This one donated a hydrogen. This one is a proton donor. And that makes this the acid. So that leaves this one. What happened to the water when it moved from this side of the equation to this side of the equation? Did it gain or lose a hydrogen? Well, it went from H2 to H3, so it gained a hydrogen. This is our proton acceptor. Also known as our base. Our acid becomes our conjugate base. And our base becomes our conjugate acid. Why? So most of the time you won't see an arrow like that in acid and base equations because acid and base reactions tend to go back and forth until an equilibrium is produced. So it's not like a typical reaction where you're going to add A plus B and that will give you some type of product. And the product is what you end with, and it's pretty much irreversible. These go back and forth. And as soon as you have more hydrogen ions, it'll shift in the more acid direction. If you lose hydrogen ions, it'll shift more in the base direction, and it kind of goes back and forth until you reach an equilibrium. That type of arrow is indicated by like half arrows that look like this. So this one's kind of pointed in that direction, this one's pointed in that direction, and it's going to go back and forth. So if instead of going in this direction, like how we would read a normal equation, if we were to go back in the reverse direction and we went from here to here, we could see that H3O becomes H2O. Now this would become our proton donor. That's why we consider this the conjugate acid, because on this side, when we're going in the reverse direction, it becomes a proton donor. Same thing with this one. When we go in the reverse direction, over here, Cl is actually going to pick up a hydrogen. This becomes a proton acceptor. So we have our acid and our base, and then we have our conjugate acid and conjugate base. And this basically just describes what I went through: acid, base, conjugate base. Ammonia is a weak base that forms the ammonium ion and hydroxide ion in water. So here you can see NH3 becomes NH4. NH3 gained a hydrogen. So this is our hydrogen acceptor. Hydrogen acceptors are considered the base. H2O went to OH. It lost a hydrogen. It donated a hydrogen. So when it moved from this direction to that one, it gave up a hydrogen. This is our hydrogen donor. This is our acid. So the conjugate acid-base pairs are NH3 to NH4, H2O to OH. So here are some more examples, and these are all labeled out for you so that you can see which is the acid, which is the base. My bit of advice is look for any atom that's not hydrogen or oxygen to start out with. So for this one, I'm going to look at the N on this side and see what happened to the N on this side. When I went from the N on this side to the N over here, first I had 3 hydrogens, now I have 4 hydrogens. This makes this guy the hydrogen acceptor. And because it's a hydrogen acceptor, we call that the base. Now we look at the F, the fluorine. When I had F over here and I went to F over here, what happened was I donated, I gave up a hydrogen. So because I'm giving up a hydrogen, I'm a hydrogen donor, this is classified as an acid. Now if we're going to go in the reverse direction and we want to go from the N over here to the N over here, we started out with 4 hydrogen, but we gave up 1, we donated 1, and we became NH3. That's why this is considered the acid. Now over here, if we're going to go from this direction to this direction, we started off with fluorine, but we picked up a hydrogen as we moved to this side of the arrow. That's why fluorine in this example is considered our base. And you can go through each one of these because they're labeled for you and figure out what the acid is and what the base is. So in this example, I'd like you to determine whether these are acids, bases, or salts. Acids typically begin with H. Bases typically end in OH. And a salt is just a metal-nonmetal combination. So go ahead and pause the video, go through this, and determine acid, base, or salt for each one of these. Okay, so for this first one, NaCl. So this doesn't start with hydrogen, doesn't end in OH. This is just your typical salt. KOH. It ends in OH, so it's a base. HCl. It starts with an H. This is our acid. MgOH2, it has that OH, so this is going to be a base. MgCl2, there's no H or OH, this is just a typical salt. And H2SO4, it starts with H, so this is our acid. What is the conjugate base of hydrogen phosphate? So first we have to figure out what hydrogen phosphate would look like. Hydrogen phosphate is H plus and PO4 3 minus. When we flip down the charges, this becomes H3PO4. Now they're asking for the conjugate base, which means this is the acid, which means this is going to give up or donate a hydrogen. So if H3PO4 donates a hydrogen, it becomes H2PO4. And we put this minus up here because when you're donating a hydrogen, you're becoming, you're losing that positive charge, you're becoming more negative. Okay, so go ahead and pause the video and identify each as an acid, base, conjugate acid, or conjugate base. Okay, so if we look at these, we have water and water. So we can label either one of these as an acid or the base because it's the same thing. Water can act as both. In this instance, when this water comes over to this side, this has gained a hydrogen. Sorry, we're going to make this one, the acid is going to go over here. Let me erase this. There we go. So if we want this to go over to this side, and this one to go over to this side, anytime you accept a hydrogen, If you're a hydrogen acceptor, a proton acceptor, you're going to be a base. Anytime you donate a hydrogen, you're going to be an acid. So this one gave up a hydrogen, accepted a hydrogen when it went from this side to over here. This one in this instance is going to actually be our base. Because it's gaining a hydrogen, it's a hydrogen acceptor. This water over here went from H2O and it lost a hydrogen. It donated a hydrogen. So in this example, this is our acid. Now if we're going to go into the opposite direction, and H3O is going to come back to here, and OH is going to come back to here, when H3O goes to H2O, it is donating a hydrogen. So this becomes our conjugate acid, and OH accepts a hydrogen. This becomes our conjugate base. The base will always become the conjugate acid, and the acid will always become the conjugate base. So let's look at this next one. So we've got some H's and O's, but this sulfur is what we can identify on both sides. So if we go from this sulfur to this sulfur, we went from H2 to H. We gave up a hydrogen into solution. So since we donated a hydrogen, this is considered our acid. Now when we went from OH to H2O, we accepted a hydrogen. We gained one more hydrogen. So this is our base. If we're going in the reverse direction, when we go from here over to here, we are accepting a hydrogen and gaining one more hydrogen. This becomes our conjugate base. And when we go from this to here, we are giving up a hydrogen. We are losing one hydrogen. This becomes our conjugate acid because we are a hydrogen donor when we're going in this direction. Again, the acid always becomes the conjugate base, and the base always becomes the conjugate acid. Looking at this next example, we have S and S. This 2 minus it's not supposed to be 42. That's just an error in how the problem is written, but that's a charge and it's not necessary for what we're dealing with here. So we're going to go from HSO4 to just SO4. We can see that we have donated a hydrogen. This is our acid. We're going from H2O to H3O. We have accepted a hydrogen. This is our base. When we go in the reverse direction, SO4 to HSO4, we have accepted a hydrogen. This is our conjugate base. And when we're going from H3O to H2O, we are donating a hydrogen. We are losing one hydrogen to solution. This becomes our conjugate acid. The next problem, so this is kind of the reverse of what we saw up here. So we have this one going here. When this one becomes H2O, it gained a hydrogen. So this is our base. When H3O becomes H2O, it lost a hydrogen. This is our acid. When we go in the reverse direction, H2O back to OH, it is going to lose a hydrogen. This is our conjugate acid. And when we're going from H2O up to H3O, we are accepting a hydrogen. So this is our conjugate base. And this last example here, we have N and N. So when this N goes over here, it gained a hydrogen, so this is our base. When this H2O goes over here to OH, it lost a hydrogen, so this is our acid. When this NH4 goes in reverse, it is losing a hydrogen, so it's a hydrogen or proton donor. This is our conjugate acid. And when OH goes to H2O, this is gaining a hydrogen or accepting a hydrogen. This is our conjugate base. So which are the two Bronsted-Lowry acids in the following equation? So which of these has the potential, if we had an arrow that we see, that back and forth, if we're going in this direction, which one of these donates a hydrogen? Well, H2 becomes HS. H2O actually accepts a hydrogen to become H3O. So our H2S is an acid. If we're going in the reverse direction, HS would accept a hydrogen to become H2S, but H3O would lose a hydrogen to become H2O. So this, in the reverse direction, is our conjugate acid. So out of these four, those two are our acids. So the Lewis acid base definition, a base is an electron pair donor, an acid is an electron pair acceptor. We don't get too much into the Lewis acid base definition, but here the Arrhenius and Bronsted-Lowry and Lewis definitions are written out for you. So you can review those as a summary of those definitions.